Hello and welcome to 5.3 video lesson number 2 for calculus class. Another amazing math video all about challenging exponential and log integrals. 4 boxes to talk about. Let's dive right into this goodness. Okay, first things first, let's do a little bit of a quick review. If we're trying to integrate a rational expression and we can't break up the numerator and denominator, then we have learned to do this thing called u substitution. And let's not forget that the goal of the u substitution is to find a u such that the derivative of u is a factor of your integrand. So like this one, for example, let's let u equal x squared plus 4. Then we know that du is going to be 2x dx. And I have a 3x dx, so I can easily make this work for myself just by multiplying both sides by 3/2. So 3/2. So if I have 3/2 du, that's an equivalent statement to 3x dx, and that's what I see in my integrand. So then I can go back and say, well, this is just 3/2, 1 over u du, which is going to be 3/2 times the natural log of whatever my u was, which is x squared plus 4, plus my constant of integration. And that's where we are right now. So hopefully this looks good to you, and this is not a big deal. And we're going to use this to sort of build our knowledge off of, okay? Okay, box number 2 is all about these 3 special circumstances of ways that we can get around rational expressions and integrals involving all this stuff here. So I'm going to show you 3 ways, and number 3 is the real special way, so pay attention to that one, but obviously pay attention to all 3. Here's our first one. We want to take the integral of 3x squared plus 2x minus 1 all over x squared dx. So if you can, it's a really good idea to, it's a really good idea to break up your fraction. So what I mean by that in this case, it would be something that looks like this. So we can take the integral of 3x squared over x squared dx plus the integral of 2x over x squared minus the dx minus the integral of 1 over x squared dx. So then we can simplify our fraction, pull our constants through. This is 3 times the integral of basically 1 dx plus 2 times the integral of 1 over x dx minus, well, this is just the same thing, 1 over x squared dx, okay? This is going to be 3x because it's our derivative of our antiderivative of 1 dx is an x. This is going to be plus 2 times the natural log of an x, which we all know now because we have the integral of 1 over x. And this is going to be minus, I lost my train of thought here. Oh, minus, remember, let's rewrite this one as the integral of x to the negative 2 dx. So, sorry, I should have done this in the step above, but I didn't. So this is going to be, when I take the integral of this, it's going to be x to the negative 1 over negative 1, which is going to make this whole thing right here a positive 1 over x. So when I write this better for you, it is 3x plus 2 natural log absolute value of x, plus a 1 over x, and then finally plus a c. So I definitely, should have done this step up here, but we kind of get the point here. The idea is if you can break up your fraction and writing it as a sum of 3 individuals, integrals, then that's the goal for this step number 1, or this first type of integral number 1. Okay, that's our first example of these that I'm going to show you. Okay, case number 2. Oops, sorry, I kind of gave the answer away here. Case number 2 is the integral of 1 over the quantity 1 plus e to the negative x dx. Now, some people would try and see this as an entire expression in the numerator, and they would try to rewrite that expression with a negative 1 exponent, but that is bad. That is bad news. Remember, the definition says we cannot take an integral with an exponent to a value of negative 1, because we're going to be dividing by the negative 1 plus 1, which is 0, and that's not allowed. So instead, we have to create a different approach. And the way that you get yourself out of this one is you're going to multiply top and bottom by e to the x. Okay, top and bottom by e to the x. So first of all, you should recognize that you're just multiplying by a factor of 1, so we're not changing the nature of the expression to begin with. And look what this does for you. Okay, this gives you an e to the x on top, all over. 1 times e to the x is e to the x. And then e to the x times e to the negative x is e to the 0, which is the number 1, okay? So it doesn't look like we've done anything all that special, but keep in mind the goal of u substitution. The goal of u substitution is to find a u such that the derivative of u is a factor of our integrand. So what that means is I'm going to let this be u. So I'm going to go over here and say, well, let's let u equal e to the x plus 1. Then du is also e to the x dx. And if I look back in my integrand, there's e to the x dx right there. That means life is good, so I can continue on and say this is nothing more than the integral of 1 over u du, because remember, du is an ex d to the x. So this is going to just be the natural log of whatever u was, which is e to the x plus 1, and then plus c. So the real trick here is figuring out what to multiply by in order to pick a u so that its derivative is a factor of the integrand. And more often than not, when you're dealing with this, it's going to be some value of e to the x, okay? So that's step number 2, or that's not step 2, but sort of option number 2 that we've seen so far. Okay, the third example of types of fancy or tricky integrands dealing with natural logs and exponents is this one. So this one's really important that we understand what's going on here. So we're trying to integrate x squared plus x plus 1 over the quantity of x minus 1 dx. And I've highlighted for you the exponent on the top is a 2, and the highest exponent on the bottom, of course, is a 1. So this is going to bring up some things that we studied way back in pre-calculus, so it's a good thing we took that class. And we're going to learn how to rewrite this a different way using long division. And the reason I know to do this using long division, and the reason I know to do this is because whenever your degree on the top is bigger than or equal to the degree on the bottom, we can rewrite this integral a different way using long division. So let me remind you how this works. So I'm going to take x minus 1. We're going to divide into x squared plus an x plus 1. X goes into x squared, x times x is x squared, x times 1 is negative x. Draw a line, and we're going to subtract. X squared minus x squared should give you 0 by design, that's true. X minus a negative x, so x minus minus, so that's going to be a positive 2x, and we bring down the 1. Now, let's start over. How many times does x go into 2x? And the answer is a positive 2 times. So 2 times x gives me 2x. 2 times 1 gives me negative 2. I subtract. So 2x minus 2x is 0 by design. 1 minus a negative 2 is a positive 3, and there's nothing left to bring down. So I could rewrite this as a positive 3 over an x minus 1. Okay? So with this information, we can rewrite this integral as the integral of x plus 2 plus 3 over x minus 1 all dx. So I'll pause right there and make sure that you can get at least that far, okay? Okay, so from here, we can break up, since we have a sum, we can break all these up and say this is our integral of x dx plus our integral of 2 dx plus our integral of 3 over x minus 1 dx, okay? This is straightforward. This is just going to become an x squared over 2. This is pretty straightforward. This is just going to become a 2x. That's not too hard to see. This can be rewritten as 3 times the integral of 1 over x minus 1 dx. And hopefully now we've realized that that can be rewritten as 3 times the natural log of whatever our u is, or in this case, it's going to be my denominator. So x minus 1 and then plus c. So all of this becomes the answer And we only get there by doing our long division and rewriting our integrand in the way that we learned way back in pre-calculus. So this one's the most complicated way because we have to remember what we did back in pre-calculus, okay? So I'm going to pause here, let you write some stuff down, and then give you some practice. Okay, here is a U-try of that third example that we just did. So I want you to use your long division, rewrite this integrand a different way, and then go ahead and go back and try and solve it like I just did for you. This should have been dx on the end as well. Okay, try this one on your own. Okay, hopefully you got the right answer. The first thing you're going to want to do is your long division, and you should have come up with x plus 1 plus 3, and then the remainder. Sorry, 3 is the remainder, but you can write it as 3 over x plus 1, just 3 divided by x plus 1. So now this entire integrand becomes x plus 1 plus a 3 over x plus 1 dx. I break up into my sum of my integrals, so x, a 1, and then a 3, and then a 1 over x plus 1. And then this goes to x squared, 1 goes to x, 3 times natural log of x plus 1, and then a plus c. So hopefully that made some sense to you. I got one more for you to try. Okay, last one here. This involves a e to the negative x. So you might want to refer back to that second example that I showed you back over in box number 2. What do you have to do to top and bottom to make sure that the derivative of your u is a factor of your integrand? Okay, try this one on your own. Okay, here is the last one. Hopefully you got the right answer. I'm going to multiply top and bottom by e to the x. That's going to give me 2 to the x over 1 plus e to the x dx. From here, I make a u substitution, let u be 1 plus e to the x. Therefore, the derivative of u is e to the x dx. I have a 2 e to the x dx in my integrand. So therefore, I'm going to multiply both sides by 2. Then I just got 2 times the integral of 1 over u du. And then we all should know that that goes to 2 natural log 1 plus e dx plus c. Okay, we'll practice more in class, but hopefully this lays the foundation for you to get a good head start.